All right, so let's talk a little bit today about transformations. Where I see my screen, okay. Um, so today we're going to go over transformations, and those include many many things that are going to be useful for you guys. So we'll talk a little bit about Euclidean transformations. So those are probably the things that you're most familiar with: move, rotate, orient. Things that you typically do in Rhino space. How we're going to do that sort of computationally. Um, um, this includes also orient, which is sort of combination of move and rotate. Then we have affine transformations, which maybe that term is a little bit different, but you should be familiar with those as well. So it's sort of scaling things, changing changing their size, not necessarily their location or orientation. And then morphing objects into place, which um, maybe you guys did that a little bit in your previous representation classes. We'll sort of go over the nuts and bolts of that, how that works. And those sort of reference more topological relationships. So the forms might be rather different, but um, topologically, meaning the same things are there, just in a different sort of configuration. Um, okay, to do that, let's first start talking about vectors. Vectors are the key to most sort of transformations in Rhino. We already know what a vector is. A vector is a direction, but then also a magnitude, right? It's um, fairly similar to a point in most regards. Consists of three numbers, an x, y, z value, and that represents the direction of magnitude instead of a point in space. Um, but the understanding of that point is storing exactly the same information. It's just how we think of that information as a vector um, rather than a point. But they can almost be used interchangeably. Um, and so we have a direction and a magnitude, but we can also get sort of unitized vector. So if we take the regular length of a vector and shrink it down so that the length is one, that's called a unit vector. So if I ever refer to a unit, that just means length of one. And these become really, really useful for a lot of calculations. When you don't need to know the length of the vector, you just need to use it the direction for several things. Reducing it down to one saves a lot of calculations. We'll sort of go through those a little bit. Um, and then if you want to sort of scale a vector in different sizes, we can do that in a couple ways. There are tools for adjusting its amplitude. Now that sets it to a specific length, or we can scale it by a specific factor. Those are different. We'll sort of go through what the variations of these actually are. Yep. Okay. I'll try to keep that. Is it any better? Let me try plugging it in here. Can you hear me now? Let's go with this one. Um, okay, and then reversing vectors, so taking the same direction of the same length of the vector, but switching its direction, so making it in the opposite direction. Okay, so let's quickly look at what that can be. So see that. So if we just have a pretty generic vector, I'll just make one, and we'll mainly be using this vector tab. You can see that you have a point tab and a vector tab, and there's constructors for both. I'll just make one with simple x, y, z, and I'll say 0.5. Okay, so just like a point, you can add an x, y, z and make a vector and adjust those. Now, vectors don't have any visualization. We might have mentioned this before. If we want to see a vector, we need to give it a specific place. Because right now it's just sort of, it's pointing in a direction, it has a magnitude, but it doesn't have anywhere to represent it. So that Rhino has given us certain display capabilities for vectors. And so it requires a base point, an anchor, and that vector. So if I want to see this, I'll give it just a simple 0, 0, 0 location, so the origin base everything off of that. Okay, so let's zoom into that so we can see. Okay, so we can adjust this vector, the x, y, and z proportionally. Now keep in mind, this is a vector and a line are similar, but they're not the same thing. So this arrow is just a representation of it. It really has no geometry. It's not really in this location. We're just visualizing it in this location. I am recording already. Thanks for reminding me. Okay, so say we have this, this vector, and we can store it in a regular sort of vector component if we need that. We can visualize it with this if we need to do that. Now let's look at some of the properties of a vector. Now if we wanted to sort of disassemble a vector or deconstruct a vector, we can get its components back out. So if we wanted the x, y, or z values for each one of those are available to us, so we can put them together and get them out from anywhere. If we want to find its length, now this gives us its length directly out of the constructor if we need that. But if we don't have that, like if we have some vector from some other process and we want to find its length, that's usually denoted with these two parallel lines. And if you see a little arrow on top of anything, that's usually a common symbol for being a vector. Okay, so the vector length, if we need that, get a panel and see how long this vector is. All right, so if we also want to unitize the vector, we have several ways of unitizing a vector. And so there are components for unit vector, which will take a vector, unitize it, Now you don't really see anything other than the numbers changing in this, but if you put a unit vector, or if you put a vector length on the end of it, you should see that length updating to 1. So now it's the same direction as the previous vector, but the length is now set to 1. So if we were to visualize this one as well, I'm just going to copy this one in and use this vector. It has a new vector that's along that direction, length 1. All right. Now, that's useful for that's useful for a couple things. Well, before I move on to the next thing, there's other ways of unitizing. So I can take usually anything that has a vector output. Let me grab another one of these, just like a simple sort of component. Now I'll just plug this in here. Anything that has a vector output, if you scroll over the right hand side of it, there's typically a unitize sort of button that you can click on, and this little symbol does that. That'll also do the same sort of thing. You don't always have to use these components. Some things are internalized. Okay, but unitizing vectors are useful for a lot of things, and you'll constantly do that for various operations. Either you want to compare two vectors directions. You want to scale a vector. If you were going to scale a vector, you can do that with simple multiplication. So if I multiply this by 5, its new length should be 5, right? That makes a lot of sense. Well, before we do that, if we had this other sort of vector and we multiply it by 5, it's just going to give you some other sort of number because its length is not sort of a unit vector. So if we want to make this a specific length, and you're using some sort of scale value to do that, that becomes very difficult unless we set it to 0. Excuse me. But there's other ways of doing that as well. That's what I mentioned with amplitude. So that's such a common operation to make a vector a specific length that we can take a vector and say, okay, we're just going to set it to length 5. Now internally, it's doing exactly what we just did. It is unitizing that vector and then multiplying it by 5, and it should have a length of 5 like that. Scoot these down so these wires don't get tangled up. Now, one thing to note, if you do get a lot of spaghetti wires and things, and you want to visualize that a little different, if you double click on any wire, this little relay will pop up, and it can help you sort of organize things. It doesn't actually do anything other than give you a little point that you can move that wire around with. Okay, so you can scale these vectors to any given length, and that's useful, and we'll show that a little bit more when we start moving things around. So if you want to move something a specific distance, you have a vector, you can scale it to a specific length, and then move that object in that direction. But as I mentioned before, the multiplication or maybe I didn't mention, the scaling by a specific factor and the amplitude of a specific factor is not the same. So if this is not unitized, purely multiplying it by 5 and sort of setting the link to 5 is a different sort of situation. So keep in mind that those vector links are going to be scaled proportional to their length or set to length or a specific amplitude. And then the other sort of thing that I mentioned was reversing a vector. So with that, that's going to point in the other direction, right? So if I have a visualization for this, I'm going to plug in this vector, it should point negative to that. So the x, the y, and the z all point in the opposite direction for that vector. I'm also going to turn, you can change your wire displays. I can make that hidden. Just assume for this lecture that all my vector displays are going to be set to the origin, so that we don't have as many wires coming through there. Now we could also set them to being faint if we didn't do that already. We have a little thin line so you can still see it, but it helps clean things up. Okay, so those get you at a couple of vector operations when you're just working with a single vector. Scale them, we can reverse them, we can change their inputs or get their inputs out, get their length. Those are all sort of good operations for us in terms of vectors. Let's see what else we can do with vectors, and more important information when we have sort of multiple vectors, what we can do with that. So if we have several vectors, we can start to use simple sort of math equations, right? We can get angles. You should understand what an angle is, right? You have two vectors, and since vectors aren't in space, no matter where you're getting those vectors at, if you get their angle, it can sort of like put these two end to end and get the angle between them. Now there's a couple of operations that we can do to angles that you might have gone over in like a high school math class or something like that, but become super important for computational design. One would be a dot product. Now you may or may not remember or heard of a dot product before. What that essentially does is it'll take one vector and project it onto another vector and give you a length. Right? So this red vector projected down onto this blue vector, and that can happen three-dimensionally in space, wherever it is. Now you could also project this blue vector onto this red vector, and you end up somewhere right here. It's going to be perpendicular to wherever that vector is. It's a little like a closest point sort of scenario, but since we're not using points, it just gives you a length along that vector of where that would hit. Now, why is that important, and what does that number actually mean? So if that value is greater than 0, so this would project down and you would get a length factor greater than 0. It's positive. What that tells you is that you have an acute angle. Now, if those vectors are perpendicular and you project down onto this angle, you would just have this dot right here, and it would have no length, right? So dot product could also tell you that two vectors are perpendicular. And if missed one. Not showing up, but also if you have an obtuse angle and you project down, you would get a length, but that length is assumed to be negative because it would basically be in the opposite direction of whatever that blue vector is facing. So you have a d value, and this d value is either going to be positive, negative, or 0. In either case, it'll give you the length of that vector projected on to another vector, but it also tell you if it's an acute angle, an obtuse angle, or a right angle. That could be useful for many purposes. But the projection of those vectors is also sort of useful for transformations in space, specifically like from one plane to another plane. Now these get used a lot in, say, robotics when you're sort of interpolating between planes. You can say, okay, I have one sort of coordinate system in XYZ at the bottom, and I have another coordinate system sort of in space, and how do I get from one to the other? Well, I can sort of project one onto the other. The other super useful sort of vector math thing that we should know is a cross product. So a cross product is interesting. Say you have two vectors, right? Any two vectors, we can put end to end, and they will be along a plane, right? That plane might be oriented sort of anywhere in space, but with two vectors, you can denote a plane. It's similar to sort of making a triangle. Two sides of a triangle will give you some sort of plane that triangle is on. So imagine you have these two vectors, the yellow vector and the red vector, and they're on some sort of plane that is sort of denoted by, say, the red vector being the x direction of that plane, and this sort of green direction being the y direction of that plane. So that yellow vector is not perpendicular to that red or green vector, but is somehow on that plane. If you can sort of visualize in that space, it's not. This is not the yellow is not the z-axis of that plane. It's actually on that plane. Okay, so if you have those two planes and if you have those two vectors and you want to figure out sort of the plane that they're on, or some other vector from that, you can use a cross product, and that will give you a vector that is perpendicular to both. So what does that mean? Well, if you have a plane and you have something that's perpendicular to both, it's going to be the sort of like normal direction, or the z value of that plane. So that's pretty useful. So you have these two vectors, and from any two vectors you can get basically the xyz of that plane, because this is the perpendicular of these two. Now, the yellow and the red are still not perpendicular, so you don't have an x, y, and z, but you could also say take the cross product of these two vectors, and it would give you that green vector that we had before, because that's perpendicular to both of those. All right, so from any two vectors, you can build a plane, and you can build the XYZ portions of that plane. Let's sort of take a look at those as well. Okay, so let's say we have two vectors, and I'm gonna copy these down. and then make some other sort of vector out of this one. Okay, we can visualize those again so we can see. Let me turn these other ones off. Let's just internalize this data so we don't have any of these. Okay, so the first vector we have and the second vector is somehow laying down underneath it a little bit. Computer's running really slow, sorry guys. Okay, so you can kind of see how those two vectors are in space. Maybe I'll just store those in components. And I'll just unitize both of them so they're comparable links. But that's just for visualization. Okay. Good. So I've made these two. I'm storing them in there just to clean it up a little bit. Now, if I have these and I want to get the angle between them, that should be the easiest thing that we can do, right? And we typically always measure the angle between vectors, not geometry. So even specific geometry, we might have to get a vector that represents, say, a line to get the angle. And don't be confused with other things. This is an angle from kangaroo. So when you scroll over, it should say compute the angle between two vectors. Okay, so we have one vector A. We have another vector B. Slide these up a little. And this angle, you'll get the angle in radians. And don't ask me why they always use radians. It's just a little easier for the computer to deal in radians than it is in degrees. And then you can also get the reflexive angle if you need it. Now, if you prefer to see that in degrees, you can run any radian number through a degree component and it'll switch it. So that's roughly 28 degrees. Between those two vectors. Now, you'll notice that the angle component also has an optional plane. As I said before, any two vectors can give you a plane. So what it's doing if you don't put anything in there is that it'll measure in the plane of those two angles. So if you're rotated in space, this is roughly 28 degrees. Now, if you wanted to measure those two angles looking down at it on the XY axis, it's going to be slightly different. So I can plug in a standard XY plane component which is just the world origin of this. And if I look at it in that sort of projection, what it's actually doing is kind of projecting those down onto that XY plane and then measuring them. So it actually gets a little smaller when it's projected, so that's only 18 degrees in that way. So keep in mind, if you plug in a plane, it may not be the actual angle between them, but a projected angle between them. Okay. Let's look at a dot product example. So we have these two. We have these two vectors. Turn these preview off. Maybe. Okay, we have these two angles, and we want to get a dot product. We want to know what is the length of one of these projected onto the other. Now they both have a length of 1 right now. So if I get the dot product, the other one, you should see that we have a 0.88 dot product from that. Well, what does that tell us? It's above 0, so we know that it is an acute angle, which is true. We can say that it's an acute angle. And the 0.88 is the length of the vector when projected on it. Okay, so how can we visualize that? Well, if we say that we get an amplitude of this angle at that length, when we visualize this point right here is going to be, if you draw a vector between those, it's going to have like 90 degrees to this. So that's the length of that one when it's projected onto that. Makes sense? We can just scale that to any sort of length of this dot product, and it'll give you this new vector from that projected vector. Yeah? Okay, say we have a unit z vector. That's going to be one that's pointing straight up. And I'm going to make it negative by adding a -1 in front of this. So this is going to be a vector that's pointing straight down. So if I use this vector is going to give me it's going to give me a negative dot product, which means that is an obtuse angle. Right? This vector and one that's pointing straight down. We need to visualize that we can. So this one and this one are going to give me that negative dot product. Right? Now, I guess it would technically be that would be the correct configuration. If this one was projected onto this one, it would come over here, right? So the dot product is 0.5 in that way. If we were going to do it the other way, find the dot product. So the order matters. If we were to say that the negative z and this one's actually, projecting the other way. And so this one would be projected onto that one, 90 degrees and negative. Okay? Now, we're thinking abstractly here. We're not really applying it to different things, but we'll go through and we'll show where we can use these a little bit more in a second. So let's move on to the cross product, because that one's where you can really start to use these to do different things. Say you have these two vectors. I'm gonna turn these things off again. So you have these two vectors again. I'm going to copy them down just to keep things clean. You have these two vectors, and you want to find a plane between them, right? I'll visualize them again. Okay, you have these two vectors. Now, if you get the cross product of one or of these two, it's going to give you the result of that is not a number like the dot product. It's going to be a new vector. And that new vector, as I said before, is going to be perpendicular to both of these. So if you look at the direction of that, you can see that that vector is now perpendicular to those. Now, the order of these matters as well. If I switch that up and say this one and this one, then it's going to point in the opposite direction, right? If you have a plane and you switch the x and y axes on the plane, it's going to flip the plane upside down, right? The x is always in specific orientation to the y, and the z is perpendicular to that. So if x is that way, y, z points up. If the x is that way and z is that way, or sorry, and y is that way, then the z points down. Okay, so we have this representation of two vectors and a perpendicular vector to that. So if we wanted to, we can construct a plane. So you have these plane constructors up here. So that a plane takes two vectors, which is what we have, and it also takes an origin. Let's use the get this parameter out for this one. So the origin, we're just going to put it the xy of this. Now we could use these two planes, or these two vectors, since we know that any two vectors can make a plane, and it's going to make a plane between those two. And the first one is the x direction. The y is some relationship between those. Right? We can also make a plane with just a single vector, which is the z value of that vector, or of that plane. Now you can tell that these are slightly different because we didn't give it an x or y, so it's just making a plane that is, aligned with that other plane, but the x and y are pointing in different directions, so it's sort of like a rotated value of that plane. But we can make it from a single sort of vector. That vector is always denoted as the normal to that one. And then we can also say if we have this, turn this one off. No, turn this one on. If we want to get some x, y, z relationship between those, we have the z value and the x value. Say we wanted to find the y value of this plane, this direction of this plane. If we take another cross product of these, say this one and this one, it should give us a new vector that's perpendicular to both. And that's, depending on if I did it the right order, it'll either be in this direction or that direction. So let's see which way it goes. So now we have the x, y, z of that plane just through using the cross products. So it's a little bit of vector math, but it's actually really useful vector math because it's doing the calculations that a computer does when getting these directions. And we'll use them a little later on as well when we're doing some analysis. When we have like surfaces and we want to pull out certain normal directions or use those, finding the slope of a surface. If we want to know how water drains or things like that, we can use these vectors and cross products to sort of determine or to visualize some of those a little more. Oh, somebody asked, can I explain what a dot product is again? Okay. Do I need to explain the cross product as well? Or just the dot product? Just the dot product. Okay, we'll go back to the dot product. Okay, a dot product, just to reiterate this, the dot product gives you, instead of a vector, it gives you a value. And that value is some sort of relationship between two vectors. In this case, it takes one vector and projects it onto the other vector. So you would find something that, whatever 90 degrees to this blue vector to this point. And then the length of this is going to be the dot product between these two vectors. And as I mentioned before, the dot product is useful because you can, depending on if it's positive, 0, or negative, it'll tell you if it's a acute right angle or obtuse angle. And then it's also pretty useful to if you're going to do sort of transformations of planes to other planes. So if you have one plane, you have another plane, you can use the dot product to say, okay, how would this project onto that on the x, y, and z value? We won't get into that, but just to know that it's a useful tool to be able to do some of these calculations. Okay. Where were we? Cross products. Planes. We touched on planes a little bit. So planes, especially when we start moving and reorienting things, they'll usually use plane or frames as ways of reorienting objects. Since a plane has not only a position and a direction denoted by these axes, with multiple axes you also have an orientation. And so if you orient an object from one position to another position, it'll change not only its location but also the direction of rotation. So that's really useful also for robotics to say, okay, I want the tool to be in this orientation, or I want it to be in that orientation, as well as other things. If we'll go through various examples of where we want to take an object and sort of place it along a surface, and as that surface sort of changes its orientation, we can map directly to what that new orientation is. And things like rotations are often sort of noted as like rotational around the plane, because it will use that normal axis as the rotation axis. You might also have like a line or something. But, okay, so let's do a couple examples. Simple ones that you might want to do: moving, rotating, orienting, things like that. Let's see what that's like. Okay, so everything turned off. I'm going to take I'm going to make a simple sort of cylinder, just to have some sort of geometry to move. And by default, it just makes it at the base. And right now, that's an open cylinder, and you can denote its height, its radius, and where its location is. We'll just leave it at the default to show what we're doing. Okay, so we did a move before. We mentioned that we don't copy things, we move them, and it creates a copy by default. Okay, so if we have this cylinder and we want to move it, we can say, let's move it in the direction of one of these vectors. Just use these as our movement vectors. So that vector is going to sort of move from this plane up until some plane that describes that new location. Now, if we wanted to adjust that, we could say use the amplitude. Say we wanted to move it 5 away. So that's kind of scaling where that is along that vector. Make sense? Yeah? Okay. Let's just cap this. Some closed. Okay, so we've moved along this vector 5 units and made a new cylinder. Okay, let's do a rotation. Say we have this object and we want to rotate it. Now there are several rotations. I'm not going to use that one. I'm going to actually click on it so you can see them, because there's rotations in different sort of plugins and things that we have, so I don't want to confuse you. So we have, if you click on the transformation tab, you'll see a couple of different things. You'll see the Euclidean transformations. You'll see affine transformations, morph, and some utilities as well. Under the Euclidean, you see that you can rotate an object in a plane, so around its sort of z-axis. You can rotate it 3D, so you can give it a center point and an axis denoted as a vector. You can rotate it around an axis given as a line, which has, you know, a start point, an end point, and you can rotate an object from one direction to another. So that would be sort of taking two vectors and saying what is the angle between those, and, you know, rotating it like that. So all of these are basically using the same information, just with different sort of inputs for getting that information. So a plane, a vector and a point, a line, and two vectors can all be used to make sort of planes or get information out of them. Let's use the rotate 3D. So if we want to rotate this, our geometry plugs into G. Our geometry plugs into G. So you see by default it rotates it around the origin. And we need to give it a couple things. We need to give it the angle in radians. So by default, it's 90 degrees, 0.5 pi. We need to give it a center point. And we need to give it an axis. So if we say we want this to be the axis, it's going to rotate it in place around its base. So it rotates left or right by 90 degrees. If we want the center point to be some other random point, if I were to bring in another random point, over here, it essentially treats that like a plane with a vector pointing in that direction and rotates it around that. And say I wanted to rotate it 45 degrees instead. I can't just plug 45 into it because it's going to actually, 45 radians is quite a lot. But most things that require radians, if you click on them, you'll see an input to change that to degrees. So that's maybe easier to understand. Rotating around that line, that point. Okay. Now say we want to rotate it around its center point. We could use the volume component to get its center point, like we did in the previous class. And so instead of rotating it on its base, it finds the center point there and rotates it. Okay. All right, great. These are all like super sort of basic understanding of how to, you know, move and rotate things in Grasshopper. If we want to do more interesting things from it, we sort of need to build these and put them together in different ways. Okay, so let's look at an example for orient that's maybe a little more interesting or more applied. Say we have, I'm gonna just copy this surface over. On Canvas, you should have these exercise files or the example files, which has all of these things already in them. But it has a surface that I just made. Simple sort of lofted surface. Nothing special. Now say I want to take this cylinder and I want it to follow this surface, right? Well, I know I can orient things. Remember, orient is some sort of combination of move and rotate. If I have new plane locations along that surface, I can say move from wherever its current position is to its new position with this new rotation. So I somehow need planes along this surface. Let's say surface frames. That'll actually take a surface and give me a certain number of subdivisions. Yeah, maybe that's good. And then orient will allow me to take whatever sort of geometry. I'm going to use this cylinder with capped ends. And I'm going to translate it or reorient it from this origin plane to this new plane. So you can see if this plane were to match this plane, then this cylinder would stick out at an odd direction, sort of perpendicular to the surface. So I can say this is the geometry that I want. The plane is going to be this origin, which, let's see where, right now by default it's the XY, so that works for us because it's built on the XY. If it was built over here, we'd need to make some sort of plane at the middle of it on the bottom, but we can use the default for right now. And then if we plug in this as this new position, oh, no, sorry, we don't want that surface. We want this cylinder. If we plug in this new cylinder to all of these positions, it's gonna basically remap those along the surface. You can see each of them is kind of perpendicular to that and is reoriented. The scale should be exactly the same. It's not changing the scale of anything. And if I add more sort of division, say I want 20, the U and the V are just going to be the numbers in different directions. So I can say 20 in that direction, 20 in this direction. So that's a bit much. Let's make it 15. And you can see that it's not an even distribution of this because it's actually, we'll go over this a little bit, or I think if we have mentioned this already, the U and V directions of the surface. So because this surface is sort of stretching out over here and condensing right here, these sort of map to the UV directions of that surface. Get rid of that one, just come back to this. Okay, great. So we can take objects and we can reorient them from a reference plane to a new plane or a new set of planes. So this one maps it because this is a tree, or this dashed line denotes multiple planes. It could be a list as well, but since this is multiple planes and we're mapping from one to multiple, it makes copies of these and moves them to each one of these. Okay, so let's continue with, we've done Euclidean transformations. Let's look at affine transformations. So there we have, we typically think of affine as scaling. and we'll use a couple of other sort of resources in Grasshopper to scale in different ways. If we look and see in the transformation tab under Fin, there's a little bit more of that we're not going to go over all these, but you can scale. You can scale non-uniform. You can shear, box mapping, projection, rectangle mapping, things like that. We won't go over all of those, but they're working in similar sort of ways where you're sort of transforming from one to the other, where it might change the object shape, right? This orient is not changing the shape; it's just changing its location and orientation. But affine transformations will sort of like change what that original object is. So let's do a version of that as well. I'm going to turn this on. Okay, so I'm going to do that as well. Let's make a new cylinder. I'm just going to copy this one down. Make some new proportions to this. We'll say that we're going to make the radius 10, so it's a little bigger, flatter. Turn this other one off. And let's make it a little thinner than this instead of a height of 1. It's a thin sort of disc. Okay, so let's say we want to make I won't call this floor plates, but imagine you have like several of these sort of stacked together. How would we do that? Well, we can move them. And we don't want to just move it once. We want to move it multiple times to have, several of these. So if we say make a series, and this number of z vectors, if you remember, a series makes a list of numbers by some starting point 0, stepping up a certain value by a certain number of times. So we have 10 of these. And let's make that step 2. Okay, so it starts to articulate some sort of stacking of these objects. Okay, so once we have that, we can, if we wanted to adjust its scale, some sort of affine scalar transformation that changed over the course of this stacking to adjust this shape. Maybe we were kind of like sculpting some sort of like vase-like shape. Well, let's do a scale. So we're basically going to take this geometry, oh, sorry, we're going to take this geometry. If we just scale it by its normal, it scales everything down to the center. We don't want to scale everything down. We just want each to stay in their own sort of plane and scale individually in. So we kind of need the center points of each one of these, not just the center point, the origin. So we can use the same sort of volume to get center points. and plug in a list of center points, and they're all going to scale in together. Hopefully you guys can see that. So they stay at their same level, they just scale proportionally in. Yeah. So they all have the same factor right now of scaling, which is, what is that, 0.5. So they're scaling in by halfway. But let's see if we can adjust that proportion. So when it scales, we can sort of like sculpt it a little bit. So how do we change that? Well, we could say, if we're using some sort of huge scale factor, each one of these as it scales up, in this case, would get huge, right? It scales too big to even see what's going on. So let's lower that down a little bit. Say we have let's make a domain. Construct domain and a range. So a range is going to basically say between these two numbers, I want you to divide it a certain number of times. So it's a little like a series, except you have a start and an end point and a number of steps. So we can say however many components we're copying up there, we can get the length of this list. So even if it changes, 10, so from that we get 0 to 1. We actually get 11 steps because it makes one at the start and the end. So if we were to plug this scale factor into this, you can see that it steps up in this sort of conical shape. But this top one has 2 because we have 10 components and 11 numbers. So I'm going to right click on this in and use an expression. I'm just saying whatever this number is coming in as x, I'm just going to subtract 1. So that makes now 10 numbers. Now that is exactly the same as saying this number subtract 1 would also do that. So you'd have 9 numbers. 9 divisions, so you get 10 numbers. Okay, so now this is adjusting proportionally as it goes up. This bottom one is like 0 and it steps up. Now if we want to adjust that range a little bit, so instead of between 0 and 1, we want to pick some other number. We can say say 0.5 to 0.75. And we'll make a new domain to map to this. So it's slightly more controlled. Right. Now, what happens if we don't want that to be so linear, right? It's not just flaring out or flaring in, but we can sort of sculpt it into another sort of form. Well, we introduced the idea of a graph mapper in the previous class, I think. So if we have a graph, and we pick some sort of graph that represents how these numbers might change. I'm going to use a parabolic graph. And so it's going to take these numbers and it's basically going to remap them parabolically. so that you can adjust these scalar values sort of per this graph. Make sense? So we're basically controlling those numbers. What's coming out as a linear sort of progression of numbers. Once it feeds into this, you can see it starts out small, it gets big, and then goes back small again. So that's exactly what this parabola is doing. You know, small, big, small, or, you know, flipping it around. It's going to start big, small, big. Yeah. And if we needed to, we could, you know, this is going between 0 and 1. If we needed to come into this and adjust it to say, okay, it's going to go between 0 and 2 in both directions. We can kind of scale it by what's happening in that. Okay. So that's really interesting. It somewhat gives us a mathematical control of things without having to write our own sort of mathematical equations. We could also do that through a math equation. It's a little less, you know, less visual to do that through an expression. You know, that could also be like an x squared would give you like a parabola of some sort. But this is a little more user friendly where we can scroll this around and get, you know, some sort of precise shape that we want. Okay. Okay, I want to do another example of this so I can sort of demonstrate its applicability for architecture. So I'm going to start off and I'm going to bring in a sort of curve that I've used to denote like some sort of floor plan or like a floor plate. And I'll make it a boundary surface. So it looks a little more like a floor plan. Okay. So I want to make some a tower type structure from this where I can adjust each floor individually sort of through transformations to create some sort of skyscraper type system. So I'm gonna move this floor plate and I'm gonna set up a series and with several sort of z vectors that are going to adjust how big of a building I'm going to have. So I'm going to say step, say 10 feet, and I want to do this, say 30 floors. Let's see what that looks like. That could be, you know, some sort of tower system, right? Now that's just a straight, almost extrusion of a building, so we can do better things than that. Okay, so let's say if we wanted to be able to scale these components, so I can use scale, use this geometry, and then if I do that, then it scales it down to the center. So I need an individual center point base to scale each one of these that keeps it in the same orientation, similar to how we did with the cylinders. So I can use an area component each one of these since they're planar, and give them center points. So now these all scale down. Let's turn this original around. And I want to control that a little bit more. So I will, I'll make a factor, and then I want the factor to be somewhere, let's say I want to scale it between 0.8 and 1.25. So I'm going to create a domain, and I'll say construct domain, and I want to say 1.25, and I'll have that be the upper, actually the lower domain, and 0.8 will be the lower domain. So anything, I'm going to use this to remap the numbers, and so anything that's low is going to turn to like the higher range, and anything that's higher is going to turn to the lower range of this. And so I could set this to be, say, associated with some sort of domain or some sort of range. And I want to make a different number for each one of these. So I need to know how many numbers there are. So I'm going to say the length of this list. And remember, we have to subtract 1 so that we end up with the right length of list. So now this is going to give us, we need a domain. Don't need to look for that list. We need this number. So 29 objects, 30 numbers. So if we were to plug this in, we would end up with it scaling like this from 0 up to 1. We want to remap those numbers. So if these are the numbers, we want to remap that between, this is 0 to 1, to this new domain. So let's see what that looks like. Okay, so now we can play around with, the top is scaling, the bottom is scaling, and we can set what that is. Okay. So if we do that, now let's add a little bit of rotation to each one of these. So if we were to rotate around in the same axis, we have each of these floors, we want to set some sort of rotational value. And we want to set a line that we're rotating around. Okay, so let's see if we can set up this range that can also be the same sort of range for this. If I set this domain instead of 0 to 1, set it to 90. And I set this domain also to 90, it'll just remap it to the same number again. But then I can use this number to say, okay, I want to rotate it by 90 degrees as I move up. So I can use this number as rotation values. I'll set it to degrees. Now this is rotating around which axis? Some line that I haven't defined yet, so you can see how it's rotating actually an interesting way, but not for a skyscraper. So let's define a line in a different way. If I have a line, I can define it. Let's define a line by a start, direction, and length. So I can create a point at just the origin, 0, 0, 0. And I'm going to say that line is just going to move vertically, which is what we want. Okay, so now we can rotate around that. So I have a tower that rotates 90 degrees as it moves up through that. Because I've set this domain to be from 0 to 90, I know the bottom one's not going to rotate at all, and the top one's going to rotate to 90, and all of these are going to be in between. So if I adjust that, I can I can set them to move in relationship to each other. Great. Now let's see if I wanted a little more control over those. Say I don't want it to be so so consistent of a rotation, or at least not such a linear rotation that it just rotates in one direction. Then I can maybe adjust those. Make a little room here. Let's move these up. Trying to organize it a little bit better for you guys. Okay, so we have this value for the rotation. If we wanted to adjust, we can use our graph mapper again. We have values that are coming out of this domain. And we have, let's run it through, say, a Gaussian curvature. Now, if we look at those values, what's coming out is going to get remapped between 0 and 1. Now, we know the rotation that we want is more like 0 to 90. Or we can change it to whatever number we want. I'm gonna double click on this and just set this. Let's just set it to 100. Just gonna remap those instead from 0 up to 100 and then back down to 0. Let's see what that does to our rotation. This gives us a little play in how this rotates. So we can rotate the middle independently by this graph. We can get it to rotate anywhere along that. This looks like a snake when we start to do things like that. We can also determine how much it rotates. So that graph can be really useful for doing things like that. Now we could also do that for, say, the scale factor, or if we wanted to move them. We can do that independently. We could associate each one of those transformations with an image mapper and like its RGB value, so you can explore those a little bit more in your assignment. Let's go back to our surface example. I'm going to turn these off. We have the surface, and we have these frames. I'm going to copy this down. say we wanted more fine control over some of these objects. I'm going to say I want this to be around 75 divisions this direction and 100 in this direction. So we got a lot of planes on that. And if you wanted to change the display of that, if you wanted to see every last one of them, you can change this. Right now it's 1. We probably have to make it smaller than that to show up. But you can see that those planes are just more stacked in there. Okay, so let's say we make do I mean graph mapper? Did I say something else besides graph mapper? Okay. So say you wanted to make circles on all of these planes. Make circles on this plane. Going to be a bunch of circles. And let's see, for radius we could make it maybe a lot smaller so you can see all of these. Okay, so we have a bunch of circles across this surface, and they're following that surface. And say we want to adjust them by some other sort of parameter. Let's arrange these a little bit. There. And I want to take in some sort of like image. So Grasshopper lets you bring in images with an image sampler. And I've loaded a couple of images for you guys to just like test. You can come in, click on the component and say image, and it'll bring up some sort of box. You can find these JPEG images on the module and canvas. I'm just going to use some sort of sample. Say open that up. What that's going to do is going to load an image, and I've made these images just like simple sort of black and white images because I'm going to use the value of the image to denote the change in value across the surface. So if you think of this square surface being represented in this square image, each sort of UV value along the surface could be denoted by some pixel along this surface. So they have very similar sort of representations, even though one's an image and one's geometry. I can get information out. And depending on this color, I can say, okay, what is the gradient value along this surface? Is it black? And I can set that to either 0 or 1. And white would be the opposite. Right? So I'm going to say for each one of these UV values on this surface, I'm going to plug it into here. And I'm going to get some number out of this. Now, a trick that you need to look at is just like when we normalize a vector to make it between 0 and 1, we want to reparameterize a surface. And I might have mentioned that in a previous class as well. That's basically setting the bounds of this surface from 0 to 1 in both directions. So it kind of matches what this image is showing. So let's see what happens, or let's see what this value is that's coming out of here. So it's going to get this basically black and white value at each one of these. So it gives me a number that changes over that surface. That's black and white, so they're all going to be the same number. And if I were to use that as a radius, it would make this radius associated with this number. Now, you can see the radius is quite small here, so I don't want these to be giant. So I'm going to remap these numbers. And if you remember what remap does, it takes some sort of value, initial value, and it sort of changes it from one domain to another. So this one's going to be some sort of value. I don't even know what the bounds are. If I right click on this and I say, oh, not right click on it, left click on it, I get this little image sampler thing. So this one I can say what information do I want to get out of this? So in this case, I can say RGB colors, the red value, the green value, sort of alpha channel, color, hue, saturation. I just want brightness. Brightness is a good sort of value. So instead of 3 numbers, I should get 1 number. There. So that's actually remapping. It should be between 0 and 1. So let's see what that actually comes up with if I change that to switch to top view. And I can see that this is stretching this image out across this array of circles. It's also changing these values for the radius of the circles to match this sort of value that's coming out of here. Now I can adjust that. Say I'm going to change the domain. I can come up here and just click on the new domain that I'm going to control more independently from this. So if this value is between 0 and 1, I'm going to set a new value. So I can scale that down. I don't want it to get so big that these circles overlap. So I can set the ones on the outside to be so small and the ones on the inside to just be crossing a little bit, so I can see that gradient a little bit more. All right, let's turn this. Turn this off. So these are following the surface. You can kind of still see the underlying surface behind that, but I'm actually using this image to map sort of the radius of these geometries. Now I can plug in different images to this. If I come back to this and say change the image, I can try a different sample. So sample 2 is, I just made a bunch of different gradient sort of patterns that I could use. And so you can see how that sort of maps to it. This edge over here and this edge over here are related to this edge and this edge. It's probably more in this orientation. So if I wanted to, like, say this was, some sort of paving pattern or, facade or something like that, I could basically paint an image of what I want it to be, and this would sort of adjust it. And I can do this with more than just scale, right? I can do this with rotation, like that value could be mapped to angle. I could do it with like the size, scale. I can use any of these transformations. Moving along a vector, I can move it in the normal direction of that surface by a certain percentage. And so then I can control it not through like a slider, but or some sort of mathematical formula, but more like colors and pixels. Now I'm going to put in I also put in an image of a person, Mona Lisa, just so we can see how fine these values can get, and how pixelated image can get. When it's over gradient, it doesn't really matter. So that allows you to start to map things. You can see in this case it's the negative, because whatever's dark here is actually becoming small. So if I wanted to flip those around and say, okay, the smaller value is going to map to larger ones, then I can change that to be more like the image that's showing up. And this is still mapped to three-dimensional geometry as well. So the image sampler is really interesting and allows you to do some really nice sort of things, either bringing in images of different stuff, or sort of using custom JPEGs as kind of like maps of different values that you want. Now, if I wanted to change this, like this is actually a color picture. It's just taking the brightness value of that image. So if I bring up the I can also change that brightness to, say, an RGB value or something. If I wanted to pull that out. So if I change this to an RGB value, and like before I had 3 numbers that were all the same, I would have 3 different numbers. So I could take that color and say, get the R value that's going to adjust, maybe that's the scale. Maybe the G value is going to adjust your rotation. And the B value is going to adjust some sort of like movement. So I can do multiple things from the same sort of image depending on that sort of the values that I'm getting out of it. Keep that in mind as you get your assignment a little bit later on how you're going to do these things. Oh, somebody said there's no modules under. Let's fix that. Okay. Sorry about that. Okay, so we've gone over affine transformations, at least scale, graph mapper. Let's talk a little bit about morphology. Morphology is a little different. As we move into like discussing sort of like morphing as a transformation, what's actually happening? So in the 1700s, guy Johann Wolfgang Goethe created this theory of morphology. And so through this, he wanted to understand the various biological forms that were out there, and how their relationship ties them together, and also their development, how things sort of grow, and so they're somewhat related, even though their geometries, are not the same. They're sort of variations of a single sort of system of geometries. And so, as architects, we are primarily concerned with form in this respect, and so it was interesting because it started to set up a distinction between like a fixed form and a formation process, or like a system, an overarching like system governing form. And so, it's gonna play. This is a project by Andy Lomas. He's a computational sort of designer that deals super slow. Speeds up a little bit. Um, so this is a series by Andy Lomas, and he deals with sort of cellular growth of forms. And so it's just made out of simple spheres, but through the complex interaction of these things, you actually generate several different forms. And he wanted to start to articulate how cells sort of grow in living things. So the cellular division. Oh man, this is really difficult to read. I'll put the link somewhere for you guys so you can actually find it and watch it a little better than streaming over this. But he didn't really make these specific forms. He just generated the process in which these forms were made. So he didn't know what the output would be. He would say, okay, I want these things to divide and have certain rules for it. And then by iterating over that, he could generate, pretty complex sort of situations. Could one of the TAs just Google search Andy Lomas in like cellular forms and see if you can put a link into the chat so you can watch that. It's a little tough to see over this. Okay. So this started to represent biological forms, how they start to divide cells and sort of the rules that generate the form in natural systems. And that's a process that's called natural morphogenesis. And so what are all the conditions that affect the way this form is developed? Okay. And there was a guy called Darcy Thompson, super famous biologist. He wrote this book called On Growth and Form. And it's a book that I reference quite a bit because it starts to set up the underlying logic for morphological changes in computational design as well. A little bit how we use, our surface logic, right? The sort of UV directions of the surface and how that can stretch and change and adjust the sort of parameters of that surface. And so he created certain geometric laws that shape the relationship between like multiple different forms, right? You have several different fish species sort of mapped to this grid underlying like logic that controls morphological changes. And so he could associate different fish forms to each other by distorting this grid. All the fish that he put into this had similar sort of characteristics. They all had a mouth and eyes and fins and gills and were a certain length and size. And so by taking a somewhat generic fish form that had all of these and distorting this grid, you can get a wide variety of fish forms. And so this laid the groundwork for sort of parametric or associative logics in that way. He also used this Cartesian grid, which was extensible and transformable, like not only globally but locally. And so we'll sort of reference this. We're talking more about surfaces. But you can see this sort of transformation when looking at like a human skull and say a gorilla or monkey skull. Through transformations in that grid, you could basically map three-dimensional form from one object to another that had similar sort of topological variations. And this is another video that sort of shows that, but it's not playing very well over the internet, so I'm going to continue. Maybe. Okay, another another thing I wanted to explore was the box morph system that we were talking about in class. And so I'm going to bring over some sort of object that I've made. You see it's tiny. This object is going to be kind of like a brick, and if I look at it, it's just in a 1-by-1 box. The size of it at this scale doesn't really matter because we're going to scale it proportional to boxes that we apply to a surface. So this can be a larger sort of tessellating object. Okay, so let's look at what we have to do for that. I'm going to bring in one of our surfaces that we looked at before. And this is just that surface that that we had here. And so something I want to do, I want to create some sort of bounding box from this. So bounding box. And that's going to be a guide for how I'm going to map these to the surface. And because of the way I've made this geometry, I have some surfaces up against that box. And if I map this to another object right next to it, where these surfaces are coplanar, then this side would match up to this side, and I would have some continuous tessellating form between them. Now, watch the video that I've included on Canvas to sort of see how I've made this. It's not specific. You can make sort of any form that you want, but I've made this geometry specifically to tessellate, so the surfaces flow from one sort of object to the next. You can determine how you want to make your sort of bricks or units for your wall. Okay, so I've made that, and then I need to divide up. So that's a unit and the box that's surrounding it. I need to make boxes along the surface to be able to map to that. So I can make a surface box. Now that will take a surface, and you need some sort of division, a domain. And for surfaces, we need a domain 2D. Let's see. Construct 2D domain. Or actually, no, we don't want to construct a 2D domain. We actually want to divide the surface into multiple domains. So I'm going to say divide domain 2D. So what this is, I'll use the surface as a initial domain. And since it's reparameterized, its domain is going to be between 0 and 1 in both the U and V directions. And I'm going to say I want to divide it say 7 by 7 grid. So that's going to give me new domains for that division in a similar way that the domain and range work up here. So you can see once I do that, I get all of these boxes that are sort of following the surface, where the tops and bottoms are all sort of attached to each other in this frame. Now this gives me individual boxes that are called twisted boxes because they're not 90 degrees anymore. But that's a sort of framework that I can use to map these things. So I'll come over here to box morph, and you can see from the picture it takes a square box and maps it to a twisted box. So the geometry that I want is actually this geometry. The reference box is going to be its own sort of bounding box. And the box I want to map it to are these surface boxes. So similar to the way we were reorienting the cylinders to the surface, we're going to have multiple boxes that we can then morph this object to. So when I plug this in, it's going to go through and make all of the components along the surface. And if you have too many of them, it'll take a long time, or if your component is fairly complex, it'll take a long time. I'm going to turn this object off. I don't need to see it anymore. And I'm going to make a custom preview for this one. Make it look. Okay. So you can see that this is a kind of repeated pattern where these sort of sculpt across this surface in some way. Let's see what it looks like. Great. Okay. Okay, so we have this sort of object and we're mapping it. That means that each one of these is a completely different geometry. They're all stretching out and sort of bending and folding across this surface. And depending on how many divisions we have is how many objects we get with that. So that means that all of these have similar morphologies in the sense that they're built from the same original object but have stretched and expanded to fit this new sort of form that I've set up. So what other sort of things can I do with this? Well, I've since I knew I was setting up in this way, and then this object has this ability to tessellate over multiple sort of boxes, I can do some really interesting things with it. I can create a variation of these surface boxes. I'm going to use a random list split. So I'm going to take all these boxes, and then I'm going to give it a random seed. Let's just say 5 and a value. Let's say half are going to go in this one, or roughly half and half. Somewhere in there is going to go in these two lists. So what that actually is doing is I'm going to take a generic geometry component just so I can split these up. So if I turn that off, it's randomly splitting these components into this list and this list. So I can do different things to them. I'm going to take one of these, and these are just boxes. I can deconstruct. Is it deconstruct? Twisted box corners. I want to get its corner points. So what this gives me is, you can see that if this is one of the boxes, I'm going to turn these off here, that it's giving me these 8 points. And what it is, the ABC is usually the bottom, and then the E through H is usually the top. So if I wanted to rotate that box in place, still keeping the same points, but just orienting it a different way, I can sort of rotate these around. I can say, okay, if this is 0, 1, 2, 3, and I wanted to rotate it 90 degrees, I would make this 0, 1, 2, 3. So I'm going to make a twisted box from corner points. And so I'm going to rotate these 4 points in place. So A is going to become B, B is going to become C, C is going to become D, and D is going to become A. So that's essentially rotating these around. And I can do the same thing with E, F, G, and H. So these can construct pretty much identical boxes, but their orientation is slightly shifted from what it was before. But since these boxes are being used to map this initial object to this larger surface, if their orientation changes or if these points change in the box from the reference geometry to the surface box, then they're going to map in a different orientation. So I can take these and I'll merge this list back together. So I have these boxes that I didn't change, and I have these boxes that I did change. That's going to give me all of these boxes that I need again. And I'm going to use these as the targets. Now when I do that, you'll see that this regular pattern is going to update in a way that is not so regular. Now because of the way the pattern was made, it could tessellate in both directions. The corner points align with these surfaces, so sometimes you get these circles and these paths that go through here, and they sort of wander through in different ways. It almost looks like a sort of bubble type structure. And I think I'm going to make these a little less square. Maybe this one I'll put down to 5. See if I can make them stretch out even more. Let's see what that looks like. And so that's happening randomly. So that pattern is sort of changing by this random split. So if we change the seed to any number, it's going to pick a different sort of random configuration of those boxes to rotate. And then this pattern will then update into a new sort of random organization. Great, so that's interesting. Let's see what else we can do. So let's go back to how we're making this surface box. In a previous tutorial, we looked at the image sampler. Say we wanted to make a new sort of offset box, and I'm going to close this down for now. Say we wanted to take this surface and I want to somehow move it up proportionally to some sort of image value, a Euclidean transformation. I'm going to take this surface and I want to get some points from it. So I'm going to use, let's say, divide surface. It's going to give me a bunch of points here, and I can say how many I want. Maybe I have 50 divisions in this direction, 50 divisions in this direction. It's going to give me plenty of points to work with. Now, I'm going to take an image sampler, and I'm going to use one of the images that I included on Canvas. Let's see what we have. I don't remember what any of them are. Okay, this one. So I'm going to plug these UV values into here because this is where I want to take these samples across this surface. And then from that, I want to be able to get out some sort of value that represents, like a height map to be able to move this surface. So I can say these values that are coming out of here are going to be associated with color range. So I want to change that to brightness, so I get one sort of value, and then I'll create some sort of move. I want to move these points by some sort of z vector. And I want the z vector to somehow be changed by these values. So I can just plug them in like this, and you can see that they update, somewhat. But I want to remap these so I have more control over that. So I'm going to remap. Should be familiar with this by now. We'll do it quite a bit now. And I'm going to construct a domain. Construct a domain between two numbers, so I can set what the maximum offset and the minimum offset is going to be. So I'll set that to, let's see what, set 0.8 and 2.5 would be. So plugging in that, you see that some of them get higher, and I can stretch that out and make the lower ones even closer. if I want to. Okay. So once I have these points, I can make a new surface from it. So I'm going to say points from surface, plug these points into here. And I want them in a single list so that they're already organized for me, but I'm going to flatten this. And if I haven't discussed that so far, it basically takes this tree data and puts it into a single list of data. Because this component itself will sort of divide up the points in the right number of divisions that I'm setting over here. So this one, I'm plugging 50 over here. That's the number of divisions, but it's not the number of points. The number of points is going to be whatever that number is, x minus 1, or is it x plus 1? X plus 1, I think. Okay, so if we have 50 divisions, we have 51 points across there. So that should give us a surface from these points. And you can see, turn off some of this other geometry. The offset is non-uniform and it's totally dependent on this. Let me see if I can, I'll switch to a different image that maybe has more defined geometry so that you can see that sort of stick out. This is that branching type pattern that you have here, sort of offset into that. Okay, so once we have that, we have these two surfaces. We can actually make boxes in between them, which is really a really interesting way of doing that. So transform, we have this blend box. So what that does is going to take a bottom surface, which in our case is going to be this surface. And it's going to need a domain for the first surface. And then the second surface is going to be this surface. And so the domain for those is going to be the same sort of division of points that we had over here. So this is our domain for this one. And it's also going to be our domain for this one, how we're dividing these things up. Okay, so you can see in this case, the domains are working. This one is a reparameterized surface. That's working across that whole thing, but this top one is not. So if we click and reparameterize it, we can do that to both of them just to make sure. You can see that we get these boxes in between that actually change their geometry as well. So these can be our new sort of boxes. I'm going to now stretch this out. So I have some room. Now these basically make the new surface boxes. Instead of having a consistent height box, these can replace that. So I can plug that into this sort of system, and we get different sort of boxes that we're mapping to. However, you can make those boxes are going to determine how it's mapped at the end. So if we look at what that gives us, it will show that sort of form responding to both of those surfaces in the same sort of way. So you can have quite a bit of control over what those boxes are doing as long as they're sort of matching up from row to row and column to column. You're going to have that consistent sort of like mapping of the object. And depending on what object you make, if it's an object that sort of goes from edge to edge, it'll fill that up. If it's not, you can still sort of change that to do different things. If I come back to this original object and I say, okay, I'm going to make some sort of torus, and that's pretty big, but it actually doesn't matter for this exercise because it's going to map to scale and orientation as well. So if I plug this into here, it'll sort of draw a bounding box to it, and then also remap this to that surface. See how well that works. Now this is doing a lot of calculations, so it's maybe takes a little time. Okay, you can see that that has updated. So these are not sort of meeting edge to edge, so it's not a continuous surface, but they're still mapping in the same way. So you can see how that geometry sort of changes. None of these are really toruses anymore. They're sort of stretching out and adapting to the organization of this box system that we have. Okay, so essentially you can use these sort of methods to create either towers or sort of walls, or in this case, it's not quite a wall, but it could serve other purposes for adaptive sort of systems across the surface. And I want you to be able to sort of make your own sort of systems using this process as well. Take a look at some of Erwin Howard's work and how he sort of creates these sort of continuously tessellating sort of units, and perhaps you can get more continuous geometry from that.